Okay, everyone, let's do question 3 from the January 22 CSEC Physics Paper 2. Okay, so the first question in part A is asking us to state the two laws of reflection. So the first one is that the incident ray, the reflected ray, and the normal all lie in the same plane. Okay, so that's our first law of reflection. And the second law of reflection states that the angle of incidence is equal to the angle of reflection, right? So whichever angle that ray hits a surface is the same angle that is going to be reflected at, right? So they're equal. Angle of incidence is equal to the angle of reflection. So there we go for 3 marks, and we are ready to roll. So for part B now, they're asking us to state 4 properties of an image formed by a plane mirror. So this is just your typical mirror that you have in your home. When you look in that mirror, what are some features of that image that you see, right? So the first one is that the image formed is the exact same size as the object. So if you look at yourself, you're going to see yourself just as you are. You're not going to be magnified or diminished in any way. It's the same size as the object, right? The image is the same distance perpendicularly behind the mirror as the object is in front, right? So those distances are the same. The image from the mirror is the same as the object from the mirror, right? Also, the image that's formed is a virtual image, which means that it can't be formed on a screen. It's not real, right? It's virtual. And then finally, for 4, the fourth property is that the image is laterally inverted. So whatever was on the left side will end up on the right side, and whatever was on the right side will end up on the left side. That's what we mean by laterally inverted, right? It's like a side-to-side thing. The sides are flipped, okay? So it's laterally inverted. That's the 4th property. All right, so that's for 4 marks. We'll be good, and we're rolling along, right? So for part C now, they're saying Maxwell washed his face at the restroom sink in his favorite restaurant. Looking into the mirror, so into the mirror, he's looking into the mirror, and in the mirror, he saw the image of the clock on the wall as shown in figure 4, right? So Maxwell is like, imagine yourself as Maxwell, but what you're looking into is the mirror, right? So we're looking ahead, and this is the image that we see in the mirror. So this is an image, right? And so in the image, it's showing us, what time is this showing us? This is showing us that it's what? That it's 10 to 2, right? That's what this image is showing that's in the mirror, that it's showing us that it's 10 to 2. So now it's saying that we should state the actual time shown on the clock, right? This is the clock image in the mirror, but in reality, what is the actual time, right? Because based on our properties that we listed up here, we know that one of the properties is that the image is laterally inverted, right? So if this is the image that he's seen in the mirror, then we know that it was laterally inverted. So instead of it being actually as it's shown as 10 to 2, in reality what it is, right, is that this arrow in reality would have been over here, right? So this little arrow would have been over here, and this big one would have been over here, right? And so if that's the case, then this is what? This is the 10, this is the 11, this is the 12, this is the 1, and this is the 2, right? So if the 2 now becomes the 10, because it was laterally inverted. So originally we know that the 2 would have been what 10 was, right? And then this one again would have been laterally inverted from what it originally was. So it would have been over here. This long one would have been over here at this 2 o'clock mark. And if it's at that 2 mark, that's what? That's 10 past 10, right? So it would be 10:10. So that's how we got 10:10 as the actual time that's shown on the clock. So remember, the feature, the property that's at play here is the fact that images in mirrors are laterally inverted. So if he looked in the mirror and he saw that it was 10:2, then in reality, what that means is that it was actually 10:10 because this becomes this and this becomes this, right? So it's 10:10 and that's for 1 mark. So we're good to go there. Okay, so let's keep moving along now to part D. So in part D, they're asking us about refractive index. And so they're asking us to calculate the refractive index. So they're telling us rather, they're giving us a definition of refractive index. And that's that N, that refractive index is defined as the ratio of the speed of light in air to the speed of light in a medium. And so that refractive index is given as this. N is equal to the speed in air to the speed in that second medium, where M means medium and A means air. So this is just the speed in air and this is the speed in a particular medium, right? So using this definition for the refractive index and the relationship between wavelength, frequency, and speed for a wave, derive the following formula. So they're saying, okay, they want us to go from here, right? This is the refractive index. And they're saying they want us to derive this refractive index in that for that medium M, right? So they're saying NM is equal to lambda A over lambda M. And they want us to derive that using this relationship, which is just V, right? Speed is equal to F lambda, right? They want us to use this relationship. So right away, we can rearrange this. So this is speed is equal to F lambda. We can arrange making lambda the subject. So we know that lambda is equal to V speed over frequency. Or we could just realize that if we're starting from what they gave us, which is that N is equal to the speed in A over the speed in M, what we could do is literally just plug in this. We could plug in this F lambda wherever we see V, right? So we plug in F lambda wherever we see V. So we introduce that wavelength that they want us to have ultimately. So we would just say V is equal to F lambda. We're going to plug this V is equal to F lambda into this original equation that they gave us. And when we do that, we end up with N is equal to F lambda A over F lambda M, right? So that's how we end up with that. For each of these velocities or speed, we plugged in F lambda M and then F lambda A. But the frequency doesn't change. As you go from one medium to another, your frequencies is one parameter that's actually not changing. That's the same regardless of whichever medium you're in, right? And so we can cancel those frequencies because they're equal. So something divided by itself, we can cancel it. And so when we cancel that, we end up with N is equal to just lambda A over lambda M. And so that's our answer. So they wanted us to prove, to derive this formula, and we were able to do that successfully, okay? All we did was use this equation, that the speed is equal to the frequency times the wavelength, and we were good to go, okay? So that's what they wanted us to do here, to show here for 2 marks. And so moving right along to part E. So part E is telling us now that a beam of green laser light, so it's a green laser light that has a wavelength 532 nanometers in air, right? Travels in water. So it's going from air and it's going into water now. And they're saying that we should calculate the wavelength of the laser light in water. So very nice. We can apply the formula that we just derived up here, right? Because we're working explicitly with wavelengths. So they want us to find the refractive index of water. That's our medium now, right? And that's what we just derived the formula for the refractive index in a particular medium when coming from air. So we can say that the refractive index of water, we know what that is. They gave us that. So that's 1.33. So we know that 1.33 will be equal to the wavelength of that light in air, which they told us was 532, divided by the wavelength of of that light in water, but this is what we're trying to find, right? So let's see all that we know. We know what the N is in water, the refractive index of water. We know our lambda in air, and we're trying to find our lambda in water. So all we have to do is rearrange, making lambda water the subject. So we'll just bring that up, and then we'd end up with the 532 divided by 1.33, right? And so when we do that, now we calculate that through, we'll end up seeing that the wavelength of the laser light in water ends up being 400 nanometer, right? So the wavelength actually decreased, right? So that's what we see here. Because we're going from air to water. Water is a more dense medium. We see a decrease in our wavelength, right? So we went from 532 to 400 nanometers. And so for that, we get our 2 marks, and we're moving right along. Okay, so part F now, they're saying that for special effects, a pool designer decides to fix the laser at the bottom of the pool, right? So we have a pool, and at the bottom of the pool, he's like fixing a laser light here, right? And so they're saying calculate the critical angle at the water air boundary, right? So bam, 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 bam. This is water down here. We're all in water here. We have the air boundary there. So this is the air up here. He's fixing the laser light here at the bottom of the pool. Laser light down here. And they're saying now that they want us to calculate the critical angle at the water air boundary. So at this boundary here, what's gonna be our critical angle, right? So the critical angle at the water air boundary is just the angle at which the light, it doesn't get refracted. It doesn't get refracted out into air, just kind of grazes along the surface. So it will like graze along this surface, right? That's what the refracted ray would do. And then so the incident ray is coming in like this to that point. We have a normal to that point. So let's put our laser light over here, our actual source point there. And so this here would be our angle of incidence, right? And our refracted ray would just graze along that air-water boundary. So this would be a 90-degree angle here, right? And so we know that when we have this kind of a setup where it's just kind of grazing along the surface, the theta I, or angle of incidence, so this angle in here, right? That theta I is actually just what our critical angle is. And we can call it theta C or C. It's the same thing. So that's what our critical angle is, and they're wanting us to find this angle here. And to do that, we know that we can always apply this generic formula, which says that the sine of the critical angle is equal to 1 over the refractive index in the medium that you're leaving from. So we're leaving from water. So this refractive index here actually represents the refractive index of water, right? That's the denser medium that we're leaving from. It's water, and we're going into air. So refractive index is for the denser medium, the one that we're leaving from. So the sine of the critical angle is equal to 1 over the refractive index of water. So in order to find what the value of C is, our critical angle, we'll have to take the inverse sine of both sides. So we do the inverse sine of this side, and we get sine inverse of 1 over 1.33. And that ends up being C is equal to 48.6 degrees, right? So that's literally all we had to do here to find the critical angle. But just remember, the critical angle is when the incident ray, the ray that's coming in, doesn't actually get refracted. It just kind of grazes along that path, that boundary, right? And that's what our critical angle represents, the angle at which the refracted ray just kind of grazes along the surface, right? Or the boundary. So then moving right along to part 2, if the angle of incidence of the laser light at the water air surface is 52, state what happens to the light at the surface of the pool, right? So we already calculated what our critical angle is from here. we know that our critical angle is 48.6. And what this really means, guys, is that this is really, there are two ways that we define critical angle typically, right? And so let me tell you the two ways that we can define it, and we'll see, you know, what would actually happen now if we have an angle of 52, right? So the critical angle, we say, is the smallest angle at which a ray can approach the interface, right? So this air-water boundary, and be totally internally reflected by it. So if we have an angle that's greater than this, then what's gonna happen is that the ray is not gonna, at the critical angle, right? At the critical angle, the incident ray just kind of runs along the surface. But if we have an angle that's greater than the critical angle, so say we're coming in here now, right? So say, let me put a different color. And this is now my 52, right? This is a bigger angle. It's coming in at like 52, just slightly bigger than the 48.6, right? And it's coming in like this. What's gonna happen is, because this angle is greater than the critical angle of 48, it's not gonna graze along the surface anymore. It's gonna actually totally reflect back in, right? And so it's gonna come right back into that medium, that water medium. And that's because, as you may be aware, when we go from a denser medium, right, to a less dense medium, the ray bends away from the normal. So this is this ray bending to a great extent away from the normal, and then coming back into this same medium that it's trying to leave, right? So if we have an angle of 52 that's greater than our critical angle of 48.6, what's going to happen is that the ray is not even going to leave. It's just going to end up coming right back in, completely, totally internally reflected is what we call that, right? And that's because our angle now, 52, is greater than our critical angle. So that's what we see. We see total internal reflection. So that's what I've reflected down here, is that if the angle of incidence, so the angle of incidence, or the angle that it's coming in, 52, is greater than the critical angle that we calculated, we'll see total internal reflection. So that's what this ray is showing us here, that we're coming right back in. We're just gonna hit the surface and then we totally internally reflect it. So that's what this blue ray here represents, okay? And that's it, guys. That's all that they wanted us to do for this question. So let me clear that. Yeah, so that's all that they wanted us to do. Again, this question is question number 3 from the January 22 physics, CSEC physics paper 2. Okay, so I'll see you in the next video.